Yeah, maybe we'll get started. Good evening, everyone, for day 2 of this online meeting on the research initiative Geophysical Flows Lab at IIT Madras. So we have 2 sessions planned for today. And as we go from the first to the second, we hope to slowly move from the ocean to the lab, all having the common theme of modeling geophysical flows. So for the first talk, it's my pleasure to invite Jennifer McKinnon, Andrew Lucas, and Sutanu Sarkar from the University of California at San Diego to give a talk on instabilities, mixing, and turbulence. Yeah.
Okay, thanks so much, Mani. Let me try to share. Is that visible?
Yeah.
Yeah.
And can you see my cursor as well?
Yes.
Okay. Thank you so much for the invitation. So this is a talk representing not just Sutanu, Drew, and myself, but a variety of other members of our groups that have been actively working in the Bay of Bengal, which are listed here. And we're going to describe a sort of broad overview of some of the interesting questions in turbulence and mixing that we've been working on in the Bay of Bengal from both an observational and numerical perspective. And so Sutanu and I will trade off. So I thought we'd start, since people come from a variety of different backgrounds here, by just describing how we measure turbulence in the ocean. And some of you are probably extremely familiar with this and others not so much. Let's see, that did not, actually, sorry, I take that back. First is just this reminder this is a nice talk that Craig and Eric gave at the start yesterday, showing all the multiple different scales of interacting. So the part that we're interested in today is this very small scale, turbulent mixing, which occurs on scales of sort of centimeters over time scales of minutes. But in particular, looking at how these very small scale processes influence the upper ocean properties, in particular the sea surface temperature, and how that feeds back onto the monsoon. So that's the part of the multi-connections that we're working on today. So again, how do we measure turbulence in the ocean? Very briefly. So we're going to look at how ask whether one-dimensional mixing schemes are missing physics that we don't understand, and what the role of three-dimensional processes are. So, okay, so we measure turbulence in the ocean just briefly by looking at statistical properties. So on the left here is a simulation by our colleague Bill Smythe at Oregon State. That's a Kelvin-Helmholtz style instability. And the idea is that once you have some sort of instability roll up and it gets going and it's fully developed three-dimensional turbulence, it has fairly universal statistical properties. And so if you measure the statistical properties within a patch of well-developed turbulence, you can back out an estimate of how strong the turbulence is through one metric or another. And so the way we usually do this is with microstructure instruments. So one example of that is shown here. This is one developed by my colleague Matthew Alford in our group, but there are similar ones by lots of other groups, and some are commercially available. So the idea is you take something like this, and I'll talk about these probes on the front in just a second, that measure velocity and temperature fluctuations. You profile it through a patch of turbulence, and you can get an estimate of the statistical properties. And these similar types of microstructure instruments can be profiled from a ship, from a profiling boat, from a mooring, or from gliders. So there's two types of measurements mostly here. The first one are the shear probes. Essentially, this is a record player needle, a phonograph needle. And as it falls through the ocean, it measures really small scale fluctuations in velocity. So you use that. The statistic people usually look at to get the estimated turbulence is the spectrum. So the Fourier transform it and look at these spectra here, an example of which is shown on the right. These have fairly universal forms. So if you fit the observed spectrum, the level of it, to one of these universal forms, you can back out the turbulent dissipation rate. So the strength of this method is that it works whether the turbulence is stratified or not. It has units of power, which is a useful currency. The challenge is that it's easily contaminated by platform vibration, so not so good for moorings. Also, the other way to do it is to use a very fast thermistor. So you're looking at the statistics of fine scale temperature fluctuations instead of velocity. So the OSU KaiPod system, which has been used really successfully in the Bay of Bengal, is an example of this type of measurement. Similarly, you're looking at spectra of temperature fluctuations and backing out the dissipation rate of thermal diffusivity chi. The strength is it's not bothered by platform vibration, so that's why it's really productive to put on moorings, profiling floats. The challenge is it can be difficult to interpret when there's a lot of interleaving fine scale temperature structure. Okay, so first question is, are there open issues in one-dimensional, how we understand one-dimensional processes? So most models use KPP, PWP, one of these things, and assume that turbulence in the upper ocean is mostly one-dimensional, driven by wind stress. Here's just one example of something that is an open question in that. These are some measurements on the left from a wire walker record, which had a KaiPod on it, Kai sensor, and there's a bunch of different quantities plotted here, which I won't go into detail, including the air heat flux, density, salinity, temperature, velocity, as this thing profiles and drifts along. I just want to draw your attention to two panels here, which is the stratification and the shear squared. So if you look at those, blown up in detail on the right, the top panel shows evolving stratification as the mixed layer is deepening. The bottom panel shows shear squared, and the stratification contours are in white. The point here is that most one-dimensional models assume that momentum and buoyancy are mixed the same way, that the Prandtl number is 1, that they are deepened and distributed, their distributions change in the same way, but the observations suggest they do not. And so that provides a complexity and interesting question to further think about. And it's a challenge for the one-dimensional models that assume that is true. Second question, I'll turn it over to Sutana here, another example of complex one-dimensional processes.
All right, thank you, Jen. So Jen spoke about the turbulent Prandtl number, and that is a limitation of ocean models. But you can overcome that if you do LES, because in LES, what you're doing is that you're resolving the larger scales of transport of both momentum and heat. So the turbulent Prandtl number in the higher stratified regions become automatically larger than 1, as they should be. So going to this particular example, so as an example, so 1D models do relatively okay in equilibrium situations. But when you have unsteady situations, like for example, the monsoon that is driving much of our work here, then you have strong wind bursts and so on. And superposed on that, you also have the diurnal cycle. And so here we show an example of LES of a diurnal cycle. And so this is a recent LES so it's inspired by Bay of Bengal measurements. And it's a moderate wind stress. So when you have a moderate wind stress, so what happens, I don't have control on the cursor, but if you go to figure 1 and then you look at, the white patch on part 1B, so the white patch in the middle there, it's basically you have convection in there. And then what happens is in the morning, when the stratification builds up, then a diurnal jet forms, and then you have a descending layer of shear. And that descending layer of shear creates dissipation that you see in figure 2, that is figure 2B there. And most importantly, the point is that if you're thinking about acid interaction and temperature changes, if you look at figure 2D, then the blue regions are the regions where you have warming of the ocean. Otherwise, it's cooling for the most part. And the warming of the ocean, the uptake of the ocean heat, is occurring in a very narrow time period. And integrated over time, of course, it builds up. And this has been challenging for 1D models. Another interesting thing that we find is that the gradient Richardson number, sorry to do this to you, Jen, 2D, it is the Richardson number, if you look at the turbulent events there, so they hover between 0.15 and 0.3. So when you have forced turbulence, it appears that the gradient Richardson number is such that you have like marginal instability. And that may be a generic feature of shear-driven flows that are forced continuously by environmental forcing. Thanks, Jen. Oh, and then this is me too. So this is a second example. So this is a meso break transition. And from part A to part B, if you look at the upper panels, then the big difference is that the wind stress, which is given in red on the header of part A and part B, the wind stress in tau W, that picks up. And before it picks up, if you go back to part A, then what happens is June 6 to 7, if you look at that rain event that Jen is pointing to, so that's that blue precipitation event, and you see a rapid decrease in the mixed layer depth in the figure there, and then the dotted line there, the mixed layer depth increases over time over a period of 6 hours. It takes a long time to increase, precisely because the wind is very low in that region. Otherwise, it wouldn't actually take so long. But the point, though, is that the turbulent heat flux Q turb, if I look at the red variation over the June 6 to 7, and then lower June 8 to 10, the turbulent heat flux has very rapid variations, and integrated over time, of course, it's responsible for the integrated increase in change in heat content. And so that presents a challenge. In fact, we have done Leah and Baylor, who are from the collaborators at Brown, and then we have Peter Sullivan and a collaborator from NCAR. So it's a joint work in here. And the 1D models we find give extremely, so there's a wide variability of the transient response, saying that, hey, when you have these transient events, then we have to be careful. Thanks, Jen.
Okay. So those were both examples of situations where the even turbulence that is nominally one-dimensional is not well understood. And then the second point we'd like to make globally is that there's a lot of three-dimensional structures that significantly influence the turbulence. And so here's one example of that. This is, again, measurements from a drifting profiling wire walker. And we're going to look at two things here. So this line that I'm pointing to here, this is near surface density. And you can see their periods. The green is a little bit less dense and the red is denser. And there are some areas where there's a sharp transition from less dense to more dense. So this is the sub-mesoscale density structure in the upper ocean. It has scales of a few kilometers, 5 kilometers, something like that. But the transitions can be really sharp. This colored line is the measured turbulent heat flux going up or down right at the top of the ocean, the shallowest bins. So red is heat flux out of the ocean, blue is turbulent heat flux down into the ocean. And the point here is that where you see rapid transitions in sharp fronts in density, for example, right here, there's a significant change not only in the amplitude, but the sign of the turbulent heat flux. So here it's going out of the ocean, suddenly it's going into the ocean. Over here it goes red to green in density, and turbulent heat flux switches signs again. So these numbers are not small. These are on the order of a couple hundred watts per meter squared. And so the point of this slide is that the small scale density structure in the ocean can significantly change what the atmosphere feels in terms of heat flux in or out. And so that may imprint those scales onto atmospheric convection patterns in ways that I don't think are well understood. So that is sub-mesoscale structures influencing one-dimensional, more or less turbulent mixing, but the three-dimensional structures in the ocean themselves can have an important influence on mixing. Amit talked about that a little bit in his talk yesterday. And here's another example of that sub-mesoscale features. Back to Satanu.
All right. So we saw in the previous slide the small scale density gradients, these lateral density gradients. And the question is that, how do they play a role when we're thinking about one-dimensional mixing, in other words, the mixed layer depth shallowing or deepening and so on. And in fact, they do play a role. And so, for example, if you look at 2A, figure A, and it shows a front, it's a density front, and it has this geostrophic shear that balances the lateral gradient. It's a vertical shear lateral gradient initially. But very soon, since the Rossby number is order 1, it spins up so to form this submesoscale eddies and little filaments. And that's kind of well known. So now what we do is that we add a convective flux on the top. So it's a cooling flux. So you develop a mixed layer with turbulence. And in part B, what we see is that these blue patches there. So these are like vertical velocity, downward velocity. And what is interesting is that now we have filtered out the turbulence, small scale turbulence. So it's the submesoscale, which is greater than 100-meter field. And what happens is that the three-dimensional instabilities, lateral instabilities, organizes this turbulence so that the submesoscale velocity field actually is larger than the downwelling is larger than without any heating. And that's a curious interaction between the two. But on the other hand, of course, since you have a front and you have a lateral density gradient, there's restratification going on. So on average, the mixed layer depth does decrease over time, but you have these, it's a very spatially intermittent process with enhanced transport in certain regions. And then if you look at part C, and part D, and we're running out of time, so I'll be just say that we have plotted potential vorticity, and you saw that in Amit's talk, is that there is a predilection for negative PV, and where you have negative PV, if you look at part D, is where the submesoscale shear, you remember there's a vertical shear, the geostrophic shear is now that energy is unlocked into turbulence, and that turbulence production can be as large as the surface buoyancy flux that set this whole process. All right, over to you, Jen.
All right, and then finally, we just have our conclusions. First one is that even nominally simple one-dimensional upper ocean turbulence driven by surface forcing can be complicated and not well understood, especially during periods of strong forcing, rapidly varying forcing, in the presence of these really strong salinity stratification layers. There's additionally three-dimensional submesoscale structures, which complicate things in a variety of ways that may be important to the atmosphere and to the air-sea feedbacks. And finally, we're excited about this new center at IIT Madras as an opportunity to continue to foster collaborations, putting together observations, process models, and turbulence theory. Thank you.
Thank you very much, Jen and Sutanu, for that fascinating talk. I think in the interest of time, we could have our discussions later on in the week and Monday next week. Thanks again. May I now invite Samin and Jayachandran at IIT Madras to give a talk on computational studies of stratified and rotating flows.
Okay.
Samin?
Thank you, Mani. Thank you, Mani. You can hear me?
Yes, Samin.
Okay, I'm going to share the screen. Okay, so I am going to present some three seemingly different problems. So I am Samin, and I will also be presenting for Professor Jayachandran, who is the main architect of the problem 3 that I have listed here. So without any preamble, let me go to the problem directly in the interest of time. The first problem is something related to the rotating turbulence. So what we were looking at here at IIT Madras was on the breakdown scenarios in axial flows. So if you look at this picture, this is a flow over delta wing. This is a smoke visualization. So you will see two of flows here, two vortices here, or one after some time of calm region undergoes some kind of instability. The other one goes into another totally different kind of instability. So this is what we call as the breakdown bubble, and this kind of breakdown is what we call as the helical breakdown. So the topological change of these vortices, which are called axial vortices, associated with the delta wing that's shown here, will have implication on the lift that is generated in the delta wing. So this was our initial motivation, but later on we found that there are similar scenarios that's in the atmosphere, in the planetary physics as well. For example, the one that is shown here, this was a picture that is of water spouts drawn by Michu. This is before the advent of photography. 1787 is when this article has been published. So Michu was associated with the weather office at the port of Nice. So he was looking at the water spouts there and identified these kinds of small breakdowns that you see in the axial vortices. So this is remarkably closer to more recent, more modern literature that's available, where you see, the axial vortex undergoes some kind of breakdown with some stagnation points here, and then you will see a bubble there, and it goes on to further changes in the topology. So we were looking at this, and to generate these things in the lab, you have a canonical setup, which is a very simple setup. Take a cylinder, rotate the top lid or the bottom lid, you get some nice vortex here, and at some particular speed of the rotation of the lid, the vortex undergoes some kind of breakdown. And this kind of setup is what we call as the Vogel-Escudier flow, because they are the first one to do this. Escudier especially did a large flow visualization of this setup. And what we have done is that we had a stratification to this. We added heat from the bottom and cool from the top, like our Rayleigh-Bénard convection. So in the Rayleigh-Bénard convection, as most of you know, there will be plumes that's coming from the hot surface, which are highly disordered. But because of the rotation and the axial vortex, everything is aligned towards the center, and then the heat transport is through the center vortex. For some, if you increase the rotation speed, this undergoes breakdown and eventually to turbulence. So what is shown here is that there are a lot of interesting regimes associated with these kinds of breakdowns, axial breakdowns, and which is one of those interesting features is rotating azimuthal waves, which is essentially caused by the sidewall boundary layers. So in the geophysical flows, this may not be present, but there are other regimes that can be correlated with the axial breakdowns. And in the presence of stratification, again, the regimes are completely different. There are bifurcations and other dynamic system phenomena that is shown here. And I am showing here some sample pictures where you have all kinds of flows, all kinds of scenarios that's present here. So I will skip this slide. This is essentially about the code. So along with the geophysical center, I would be looking at the other stratifications, the unstable stratification, stable stratification, and that the regimes in which these kinds of axial vortices break down. They're related to their relation to the heat transport and any other scalar transport that is possible. The other problem that I have mentioned in the initial slide is something on the scale space dynamics of turbulent flow. So as most of the people in the audience know, the FFT, the Fourier transform of the two-point correlation can be taken only for homogeneous isotropic turbulence. When if the flow is inhomogeneous, you have to find another way of identifying the energy. So the definition of energy itself needs some kind of tweaking if you want to talk in terms of scale space. Essentially, the energy transferred from one particular scale to another scale, and not in terms of wave number, in terms of real space. Okay, so from the physics, whatever happened, energy transfers in the physical space, which is what we obtain from measurements or observations or computation, has to be transformed to a scale space. So the energy is now, we have defined an energy which is in line with Hamba's work. Sorry, Hamba's work, where he has defined a similar energy for a incompressible flow, constant density, inhomogeneous turbulent flow. What we have extended that to a highly compressible flow, and then along with the geophysical system and the problem that I have just shown before, I we'll be looking at the stratified scenario of this transport, plus the 2-point correlation of other scalar quantities and how they transfer the energy, how they transport the different quantities from scale space. Okay. So we have attempted this and worked quite well with highly compressible flow, with especially in the mixing layer regime. And we are currently trying to look at what happens in the rarefaction. So the code that we developed because of the rarefaction, it should work for regimes that where the continuum mechanics is not valid. We have the solutions of Boltzmann equation, which is unstructured finite volume is what we have opted for, so that you can do large engineering application as well. For example, the nozzle thrusters that is ejecting the jet in outer space, in the satellite, and other altitude maneuvering. That was again the original application, but we will be looking at the turbulent scalar transport and the energy transport of in the scale space. This is another problem which we'll be looking at. This again, as I told you, it's a main architect is Professor J. Chandran, so I'll be presenting for him. Uh, this is a two fluid system where in which both the fluids are assumed compressible, and then you formulate the entire setup with the compressible flows. The liquid is again use some stiffened gas equations applicable to that particular fluid, and solve the entire system and try to get the solution. So for example, in this problem where you have a sea wave that is hitting the sea wall, there can be a trapped air in the wave, and when it hits the wall, this trapped air can undergo extreme compression, and the load on the wall is thus uh, to be calculated along with the compressibility effects that has happened there. This is one of the suggestions that has appeared recently because of the large error in identifying the load that is being applied or load that is coming on the seawall. So the formulation is done originally for granular solid propellant combustion by a PhD student, Annie Elizabeth, jointly guided by Professor Ramakrishna and Professor Jayachandran. Both of them are a part of this center. So the code that has been used is similar to what will be used for this kinds of flow, where you have a multi-fluid compressible multi-fluid system with 6 equation model, and the water, for example, in the previous problem, the stiffened gas equation for water would be used to evaluate the pressure, and then because it's unstructured, you can do a large class of problem. Uh, One problem that we have attempted, this is only the initial computation. We should not read too much into this. So we have an explosion that is under the water. Okay, so this is at a high temperature of 2500 Kelvin, and the pressure is around 10 power 9 pascals. Okay, and this sphere explodes, or we just evolve in time. Uh, the outside is temperature 3300 Kelvin. The pressure is 10 power 5 Pascal. 5G and 5G is the volume fraction of gas, which is in the region here. It's a gas, and inside here is water. So here the volume fraction is 0, outside is volume fraction 1, and then you evolve in time, and what you get is on the picture on the right side, which is an instantaneous plot. This is the isosurface of a constant, it's a constant pressure surface colored with the velocity in the y direction. And the this is the surface, which is the phi g equals 0.5 surface isosurface, and that is colored with temperature. So your temperature is high in this region, but the pressure wave has moved faster than the temperature, and the wave, the pressure wave has already hit these lower surface, but it's now expanding. So these are the kinds of problems that you could do, because now the code is done in 3D tetrahedron unstructured finite volume. You could also do, if I have a floating body here, I could include that in the simulation, or if this happens near a gulf with the land masses nearby, I can include that also into the domain and calculate the rise in water in the Gulf region due to this explosion, or and so on and so forth. Okay, so that is the problem that we would be attempting at the center. With this, I would like to end my talk. If there is time, I can take questions. Otherwise, over to Mani.
Thank you, Samin.
Yeah.
If you don't mind, we'll move on to the next talk in the
Yeah,
interest
sure.
of time, and we can have discussions
Sure.
later.
Sure.
Thanks, Samin.
Yeah. Bye.
Can I now invite Anish Subramanian from the University of Colorado at Boulder for his talk on data assimilation and prediction over the Indian Ocean. Anish?
Yeah, can you hear me okay, Mani?
Yes, Anish.
Okay, great. Do you see the slide moving?
Yeah.
Maybe not. I have to share my full screen, I think.
I can see the slide.
Oh, but yeah, it doesn't transition. Sorry, just give me 1 second. Okay. Yeah, thanks for the opportunity, Mani, and everyone organizing this event. I'm at CU Boulder, University of Colorado Boulder. I'll be talking about one topic that our group is researching on here, which is exploring the impact of ocean data assimilation to improve weather and climate forecasts. I'll just present one quick result on this. I'd like to acknowledge my collaborators on this from ECMWF in UK, as well as people here in my group, as well as colleagues in my department at University of Colorado Boulder, and yeah, other collaborators as well in India and at NCAR. The motivation for a lot of the work we do, which I think is also related to work done at GFL, is improving the information we provide at different timescales, from minutes out to weeks, days, months, seasons, as well as the climate change scenario. And the kind of information that is provided varies across the timescales, and their application also varies in different application areas in the society. A lot of the focus of my work currently is on timescales from days out to a season. So it's popularly known as subseasonal to seasonal timescale, and a prediction on S2S timescales. Here, the challenge is that the problem goes from an initial value prediction problem to a boundary condition problem as we move closer to seasonal timescale. And this timescale has been a desert in terms of getting predictability or predictive information. So being able to improve our predictive knowledge on this timescale can really help many sectors of application in the society. This is just a quick overview of the different topics. that our group here works on. The main motivation is to improve understanding of climate processes, mainly tropical convection, air-sea interaction, and then teleconnections from the tropics to the extratropics. The goal is to build a seamless system that can predict from weather to climate timescales and help improve these systems at different operational centers. One of the topics we're working on is data assimilation, and especially coupled data assimilation, where we couple information from the ocean and atmosphere. We also work on problems related to stochastic modeling, stochastic physics for convection and other processes in our climate system, and using machine learning for improving predictions. And we work both with idealized models, such as the Lorentz model, barotropic vorticity model, but also extend all the way to GCMs, extending from process understanding to actual prediction of the real world. So in today's talk, I'll be focusing mainly on like the work done over the Indian Ocean, but in a global context. As others have also mentioned, the context is improving prediction of monsoons, and here it's monsoon intra-seasonal oscillation, which is a subseasonal oscillation on timescales of a few weeks. The precipitation propagates from the equatorial Indian Ocean northward through the Bay of Bengal, Arabian Sea into the subcontinent, and all the way towards the Himalayas and the Tibetan Plateau. So being able to understand different processes relevant to this propagation and then improving our modeling and prediction of this is a motivation. As Jen and Sutanu mentioned in a couple of talks earlier, as well as other talks both yesterday and including topics that Samin mentioned, there are many fine-scale processes that determine how the upper ocean is stratified and how this connects to atmospheric convection and convective processes. And this is a multi-scale problem where you have really fine-scale mixing and fine-scale processes impacting large-scale convection and precipitation. But then there's also feedback where this then impacts the upper ocean stratification through precipitation as well as heat fluxes. So it's both a physical understanding problem that we don't have enough understanding of many of these processes, and also a data assimilation problem where we need to constrain these processes better in our model to improve their prediction. So one of the reasons that coupling between the ocean and atmosphere is important is helping improve our prediction on subseasonal to seasonal timescales. On short-term weather timescales, there's not a lot of evidence that the ocean plays a big role in prediction. It can play a role in tropical cyclones and big weather events, but as we extend out into the subseasonal timescale, a couple of weeks or beyond, we do see influence of the ocean. This is just one study showing a coupled model, which is the orange line, has an improved prediction skill over prescribing SST without coupling to the ocean, or even prescribing observed SST in the forecasts, which indicates that having a coherent propagation both in the atmosphere and ocean is important to get the prediction right. This is for the Madden-Julian oscillation skill score. So more recently, we have been working with the ECMWF model, the European model, looking at the impact of ocean data assimilation, both in the reanalysis of the ocean, as well as the prediction of a coupled ocean atmosphere system. I'll not go into the details here. We are working with the ORA S5, the latest ocean reanalysis at ECMWF. And further on, they have done work in terms of assimilating different ocean observing systems. This is just a plot from 1 week where we see most of the ocean is covered with Argo data. The tropics, we have a lot of moorings, as well as we have ship-based CTD, XPT casts, and a few marine mammal data. So what was done was a few experiments were conducted where different observing systems were withheld from the data assimilation system. So one experiment was where all ocean data was assimilated. And then we have an experiment where no mooring data was assimilated, no in situ ocean data was assimilated, no Argo data or no XPT data. And on the right-hand side, this showing the mean mix layer in the model reanalysis from these different experiments. The top is the mean mix layer in the all data experiment, and then the others are the difference between the sensitivity experiments. And what we see is that assimilating in situ observations, so the bottom one here, in the ocean has a significant impact on the mean mixed layer depth in the Bay of Bengal, and assimilating the observations reduces the mean mixed layer depth. So the model at ECMWF has a high mixed layer depth or a deep mixed layer depth bias. So then just one quick result on this, we looked at what does it do to predicting tropical cyclone energy on timescales of 2 weeks to 4 weeks. And here what's plotted is the control experiment, all orbs in the orange color, and then not assimilating the surface altimetry and the surface data. And here, in most of the basins, especially in the Indian Ocean, we see a big impact in terms of improved prediction of tropical cyclone energy when we assimilate subsurface ocean data. And yeah, so with that, I'll end the talk, Mani. We have more results which I can share with the group here in terms of meso prediction with these experiments and other predictions. So I'm happy to take questions. Mani, thanks.
Thank you, Anish. Time for a quick question, if any. So Anish, we can maybe discuss a little later. Is that okay? Thank you very much, Anish.
Yeah, perfect. Thank you.
I may now request Dr. Ashish Mitra to talk about modeling efforts at the National Center for Medium Range Weather Forecasting in Noida.
Yeah, good morning, good afternoon. So my talk is in line with what just now Anish has shown, so it will be easy for me. Thanks, Mani, for this nice meeting. Let me share this my PPT, just 1 minute. Is it visible, the screen?
Yes.
So I'll make it full screen. Is it now full screen, Mani?
Yeah, perfect. Yes.
Okay. So in continuation with almost what Anish just now said, our center also on those questions and so in how this coupling, this coupled model and ocean assimilation we are setting up. And in fact, our aim is from hours to season. We are not now going beyond season. And this center is part of Government of India's Modeling and Data Assimilation Center. And our main goal is to underpin the forecasting capability of IMD, and all the atmosphere, ocean, and the modeling is being done in this center to help IMD's forecast from shorter scale to extended range. So I'll be only speaking about the seamless modeling system. We have been working in collaboration with the consortium. And what we have put in place is the same model, unified model. It's a very good concept now. NCEP also is implementing a unified model. So that means the same dynamical core, you can use it from very small scale to season, decadal, and even climate change. So what we have configured in NCEP is the shortest scale is 330-meter model atmosphere, which is used for fog prediction in winter. Then we have variety of this 1.5 kilometer regional model, 4 kilometer and 12 kilometer. Then we have 12 kilometer ensemble prediction system in the medium range. And this data is shared in the TIGI. You can see their atmospheric model ensemble. And recently, this 4-kilometer model also ensemble, we have made a 11-member ensemble for severe weather. And the very latest one is the coupled model for the, we are using it now for subseasonal to seasonal prediction. It is at a relatively coarser resolution. N216 means 65 kilometer of atmosphere. And it has NEMO, Las Almas sea ice, and Joule's land surface model. So earlier, 1 month forecast, multi-week up to 4 weeks anomaly we were doing. But now, last monsoon, we started the seasonal forecast also, and all this thing is shared with IMD for their operational purpose. Anish showed one plot where by coupling the MJO was improving, but we have noticed that in the shorter scale also, the model is not able to capture the dry wet spell. So this is from both the GFS medium range model and the MCM or global model. So both have difficulty in clearly bringing out the dry wet spell. So this could be one of the motivation for going to coupled NWP, which ECMWF has gone in 2019. They have the 10-kilometer high resolution coupled model. And Anish described that ocean data assimilation system of ECMWF, exactly very similar system we have implemented in our NCMWF. It assimilates all kind of observations and like SST from satellite. Then these are the surface buoys from ship, mood buoy, drifter, and you have the subsurface. These are typical for a day. And the sea ice also is assimilated because the polar forecast also is being done by this model. These are the sea level elevation. So every day this is assimilation is done in real time. And what we have seen, the large scale features like the model is very assimilation focused system is capable of capturing the freshwater spread as the monsoon progresses, then the high saline water from the Arabian Sea to the Bay of Bengal and moving northward. So all the large scale features are captured well. So as I said, the model has a unified model, Joule's land surface, Las Almas sea ice, and NEMO ocean model. And these are different setup what we are intending. So I will come to the last item. We are now currently implementing a high resolution model. So what we are doing in that direction, and I think this work with Mani's group, IIT Madras, will be very useful because the shorter scale things we have to learn from this today's presentation. What I saw, large simulations and turbulence. So those are the things we have not seen yet. And with this high resolution coupled model, we are in a position now to investigate and experiment what's happening in the Bay of Bengal. And we have seen this tropical cyclone heat potential, which is part of this coupled system, is very useful. And this funny tropical cyclone you see, if you remember, it hit Odisha coast on 2nd and 3rd of May. And interestingly, this very high tropical cyclone heat potential was maintained throughout from 25th of April. This is from our ocean data assimilation system. And in the prediction also, you see a 15 days prediction was well maintained in the model. And incidentally, this NEMO model is having 75 vertical layer. So the upper ocean first 300 meters in the top has 35 layers. So the upper ocean features are very well resolved in this model. So these are the D26 depth and temperature tendency in the funny cyclone. It was capturing well, but there are issues. For example, we did some experiment with coupling and without coupling during monsoon. So if you see the top panel, coupled day 7, and these are the uncoupled on the left-hand side. And what we see, the biases, the temperature biases improves, but the salinity bias, particularly in the northern bay, day 7 is still there. So it's either the model or lack of observation, we don't know. So that is one issue which is being discussed in this meeting. So on the extreme north of Bay of Bengal, and that is the place all the monsoon lows, depressions forms, and the river discharge is there, and the stratification, your barrier layer, all the things happen there, and that is the place where uncertainty is there. And when we go to day 9, that magnitude of salinity biases actually increases. So that's the area we have to look into that. And otherwise, in the upper ocean, we have seen the coupling has a positive impact. Both the biases in temperature, salinity in almost all regions improves. But when you come to the salinity, it doesn't either you can do coupling, uncoupled thing. There's not much change in the salinity. It almost remains same. And there are issues with the analysis like the NSEP-GODAS system. So we compared this NEMO analysis with the GODAS. So there are huge differences. It's all coming due to the model uncertainty and the observation uncertainty. So this we have communicated a paper because Bay of Bengal is a region where, and we compared all this thing with the Argos data. So it seems that the NEMO based ECM development, our system is doing better than the GODAS, NSEP GODAS. And another thing is the number of observations available. So very few observations are available. On an average, you see 5 to 10 Argos are available. So we need much more observations there. Very recently, we have implemented a 112-degree eddy resolving NEMO model, global model, and these are some of the first results we started getting. So this is also L75 and 112 degree. So we'll be using this model to study Bay of Bengal, and so this is not coupled. This is only the ocean model. So our next step is to couple this to the atmosphere. But we have linked this to our atmospheric model. It's driven by our atmospheric model. So a lot of these eddies it's able to capture. So how these eddies are distributing temperature, salinity, we have to study the whole thing. And this is a smoother version of the plot, but you can see the structure of temperature, salinity, and sea surface height from the 112-degree global model. And this is interesting. We started comparing this 112-degree model output with observation. So we interpolated the model output to the observation location. So you see very few observations are actually available in the Bay of Bengal. So only when there is a one day was a clear sky condition, some satellite temperature was available there. So this is another issue. The satellite SSTs are not available during monsoon, and a lot of gap areas in observation. This is same thing with the altimeter. You can see we compared observation. So model is doing a good job, but there is a lot of uncertainty due to lack of observation. So this is the last item. We have configured a regional coupled model. The atmosphere again is part of the seamless modeling system, unified model, 4 km same dynamical core of the atmosphere, Joule's model, and NEMO ocean model at 2.2 km, and WaveWatch at 2.2 km. And we are now testing this initial idealized runs and some cyclone cases we could run. And this is the tropical cyclone, same thing funny. So this is the global model which was not doing so good. It was taking the model cyclone to Odisha coast very fast, but when we coupled it, it became more realistic. I think it will be clear in this picture. So this is the real Modi's cloud picture of the funny cyclone from the, and these are the different experiments. Atmospheric only model, you see the cyclone has reached very fast to the land, whereas when you couple it, it's slightly better, but when you couple with the wave, this is atmosphere, ocean, and wave, then it's more realistic. The position particularly looking closer to the actual cyclone. And we have seen from this run how the with depth, these are different two cross sections we took around the cyclone at this date, and you can see the impact of coupling. So this is the only ocean model. The cooling was not there, but when you couple it, cooling you can see it's going up to 60 meters. So the model, these are some initial results we started getting only 2 months back. So we think this model can be used for the study with IIT Madras group. So this is our plan that we want to now go to 112-degree global NEMO model, and this NEMO based regional coupled model which is implemented, we'll use this for process studies and particularly testing the mixing schemes here. So in fact, the land model also has a surface hydrology. So all the river can be tested, and the sensitivity, the river outflow into the Bay of Bengal, then the mixing, everything can be done there. So with that, I will finish here. Thank you.
Thank you, Dr. Ashish. We very much look forward to working with you. So we will have further discussions later on in the meeting. Thank you very much.
Thank you.
May I now invite Balaji Srinivasan, Louis Tau, and M. Ramakrishna from IIT Madras to present their work on turbulence modeling, machine learning, and reduced order models.
Okay, Mani, I'm going first.
Yeah, Louis.
Okay, let me load documents.
Yeah, we can see your screen, Louis.
Okay, good. Thank you. And yeah, I think there's some problem with my this pen is not working. So I
Okay,
cannot mark. Anyway, let's.
no issues.
Okay. How to move up? I have some problems to move my slides.
Okay.
Just tapping it doesn't help.
No, not really.
Oh gosh.
It's just stuck there.
Shall I present, Louis?
Yes. Yeah, please.
Okay.
Yeah, do I need to log out?
Yeah, you could
You can
stop
unshare.
sharing it. Yeah.
Okay. Okay.
Yeah, please go ahead, Louis. Can you see?
Okay, yeah. Yeah, now next. Yeah, and give a little bit of background about what I have been doing. My interest is about this analytical theories of hydrodynamic turbulence, and is about the flows. Okay, and now just this hydrodynamic turbulence is described by Navier-Stokes equations, right? If we use the Navier-Stokes equation and the Rayleigh's averaging, then we would get the equations like 1, right? This is for the 2-point correlations, second order 2-point correlations. And there, and you could see the red colors, right? That is equations then contains third order correlations. So this you have higher order terms in the equations of the second order correlations. And so, and then this is the so-called closure problems in turbulence. Next. Yeah, and then in 1940s, and then a Russian scholar proposed this model, this quasi-normal approximation model, and this given in equation 2, right? You can see there is the fourth order correlations is represented in terms of the second order correlations. And of course, this is formulated in Fourier wave number space. Okay, and then in the 1960s, there were a few studies. Now here I quoted one guru, and then they applied this model to this homogeneous isentropic turbulence. And then you can see the simulation there, right? You could see this part, and it's around 6, going down there, 6. And then you're going to see the energy spectrum is becoming negative. Okay, that's not physically acceptable. And then there are few these fixes to it. And people have tried a few times. And of course, there are many other these constraints, and this model may violate. Okay, and next, the big problems with this model is this whole formulation is in for homogeneous turbulence. How to go beyond, and I said to in homogeneous turbulence, and that would be a great challenge, or looks like impossible to do that. Okay, next. Money. Yeah, and then now the question is, can we use some ideas from control theory or optimization theories? Right here, let's say there. Here, let's say, right, first we can get the mean or correlation equations from the Navier-Stokes equations, right, up to the second order or fourth order. Okay, and this equation like what I mentioned before, this equation 1. And then next, then you have, we can have a bunch of constraints, right? First, like equation 3 there, right, and this Rayleigh's stress is a positive definite, right, as required physically. And then next, we have mathematically, we can generate tons of constraints that's based on the Cauchy-Schwarz inequality, the list in 4. And we can apply it to all the correlations there and to many more structure functions. Fine. And then next, we have this non-negativity of variance of products. That's essentially equation 5. And here I present one consequence there in equation 6. Okay, next. And then write all of those mean equations, correlations, correlation equations, and those constraints, all of those constraints listed in the last slide are pretty general. Okay. And now we have this flow specific constraints, right? Like boundary conditions, semi-trace, maybe if the flow is homogeneous or is isotropic, right? And these are flow specific constraints. Now, to satisfy all these mean equations, correlation equations, all those constraints, and this traditional way of use differential equations, algebraic equations may not work. And the only thing to make it work, I say the only, I'm pretty sure is the only way to make it work is adopt some objective functionals, like this equation 7. Okay, to satisfy all those constraints, all of those equations. Yeah, this objective functional is motivated by this Shannon entropy, and from the mathematical side, and then physical side is by this ceramic single of turbulence. Fine, and the argument is pretty long. Okay, I'm not going to into the detail here. And then within this framework, then we have 2 models. We can construct one is the second order model. The other is the third order model. Second order model is a special case of third order model. The difference between them is the third order model. There you will use the fourth order correlations as the control variables. Okay, next. Right, and there's so far this framework is pretty complicated. It is not too big, and then how we're going to test it, and then was okay here at this moment consider the computational feasibility or analytical and this resource available. We apply the proposed model to this 3-dimensional homogeneous shear turbulence, right? Equation 8 would give the mean velocity field that also is sketched there. And then, and this is still this model is still too big. Then we apply we do this asymptotic state. It means when the time is large, and then we cannot apply the third order model here because it's still too big. Then we use the second order model here, and we have a coarse mesh in Fourier wavelength space to make the computation feasible. And by the way, and this homogeneous shear turbulence now is essentially treated as a second order cone program. Which means that many results and the tools for convex programming can be used here. Next. Yeah, now there's one question there, right? Why we still do this ensemble averaging in the age of DNS? And then now let's look at the asymptotic state, right? Defined there. And then we have equation 6 presented before. Now we right? And then we apply the equation 6 to asymptotic state. I got the equation 9. From there, you can see the exponential rate, the growth rate should be smaller or equal to 0, cannot be positive. Okay, and now you look at the DNS data there, at least the few results there, right? Sigma 0.1, 0.18, 0.2. And so it means the DNS give the results which are should not happen, right? According to this constraint line. That result. And now I guess here maybe this DNS data give this positive sigma. I think the reason might be caused by that chaotic behavior of Lobbyist case equations. And then, of course, here, this is a complicated issue. What does this chaotic behavior of Lobbyist case equations is implications to numerical simulations? We do not know yet. We do not know that much. Okay, next. Yeah, and then now here at least the quite a few challenges, and these are because of huge computational size, hardware, software, algorithms, right? Analytical problems, or have also high dimension integrations. And we have tons of constraints which to choose. Okay, that's a big challenge here. Now we have got some partial results, and this is in the archive there. And then the results are really partial. Some are not adequate. So now I'm still testing more constraints to see whether the results can be improved or not. Okay, and the next, of course, how we're going to generate that idea to LES. Okay. Okay, I'm done. Money?
Yeah, thanks, Louis.
Okay.
So I'll go next, Mani.
Yeah, sure, please.
Let me just see. So is it visible now?
Yes, Balaji.
Okay. So I hope it's moving. So I just have about thanks, Mani, for this opportunity. So I'll just take about 2 to 3 minutes, not more than that, and just give you like a quick whirlwind tour of what we are doing. So within our lab, we work on several problems, but whatever is within the scope of this project, we are primarily working on something we call autonomous flow solvers. We are trying to develop algorithms that can mix, data, physics of the problem and the numerics of the problem by numerical analysis to see what actually stops solvers from becoming autonomous and working on their own. So specifically, we are looking to design robust numerical methods that don't show numerical artifacts, turbulence models, of course, and whatever techniques would assimilate experimental data, live data, and try to make online flow predictions. So we have found over the last 4 or 5 years that machine learning has a lot to say about at least some aspects of each one of these problems. So within machine learning, we have been looking at 2 broad approaches. The data-centric approach is the traditional approach, which is have a lot of data, build models from there, and physics is sort of coming in through the back door, or at least through the structure that you use for the model, it comes in from there. The second, which is a little bit more recent, and it has old history, but it's recent, particularly by the work in Brown's Brown by Professor Kanyadakis and his colleagues. So it's called the physics-informed neural network approach. There is a tight coupling of physics, data, and numerics directly in one sort of platform. Here is an example of the traditional data-centric approach. So this is what we were trying earlier, is published recently. And here what we were trying to do was taking something that we were working on, Lagrangian velocity gradient evolution, and try to model some terms. So here, if you look at alignment statistics, so DNS has certain alignment statistics between the pressure Hessian eigenvectors and the strain rate eigenvectors. And you can see that the traditional models don't capture that statistics very well, but machine learning captures it well. So this holds true regardless of the fact that we trained on some decaying isotropic turbulence and then tested on some other thing and even on channel flow. So, there were a lot of details here. But this was a sort of data intensive approach and also required a lot of manual handholding in order to make the ML work. So we started looking at other models also. So this is a physics-centric model. We, unlike a traditional machine learning model, which simply takes a lot of data and makes predictions. So you try to start giving physics itself as data. So the way you do that is, let's say you have a whole bunch of points. One advantage of this approach is that it's meshless effectively. So you don't need really meshes here, even for complex geometries. So you add all these points wherever you have, let's say, experimental or computational data, you specify that as a constraint. And where you don't, you actually give the governing differential equation as a constraint. So you can actually think of physics as a data. In this case, you have unlimited data because physics is satisfied at every single point. Okay. So the essential idea is to turn the original PDE into an optimization problem, which optimally satisfies the constraint of physics as well as the extra data that we have given. Now, this has tons of problems, especially for the the spatial and temporal scales that we are talking about. Even normal fluid dynamics, leave alone the kind of problems that we are handling in the GFL. So it doesn't scale very well. So we are trying to develop methods for that. And some method we have now submitted this for publication. Idea is to reduce the number of independent parameters and somehow have some kind of piecewise neural network architecture which does this. We have had a significant success with forward and inverse problems, but these are of course benchmark problems. We are now trying to increase the speed and robustness of this method and try to go right to turbulence and see if we can go. This is of course a little bit in the future, maybe a year down the line, and then try to make online predictions, maybe even nowcasting or something of that sort. So I'll stop here. Thank you. Mani?
Yeah, thanks, Balaji. MR?
Yes, let me see if I can share.
Yeah, we can see this.
Does that work? You can see it. Okay, I can't, but okay, you can see it. Very good. Yeah. So, yeah. So I am going to be talking about reduced order model. Actually, reduced order models is a very thin sliver. My interests are quite broad, and this is work that I do in collaboration with Professor Geeta Vasudevan in electrical engineering. Let me, because I know it's a mixed crowd, right? Let me just do a quick overview of what reduced order models are. So in a general situation, right? So all abstraction at one level is basically reduced order modeling. So you could have an Avogadro number of particles. Then you go through some kind of a smoothing or homogenization and go to a continuum model. You're happy. You get analytic solutions. That's good. You don't get analytic solutions, and then you're unhappy because you now have, though you have something that is smooth, it's in an infinite dimensional space, so you have, it's much worse off. So then you turn around and say that, okay, I need to reduce this back to a finite dimensional space. Typically, you do that by projecting onto some basis vector, and you get a discrete setup. And if you're able to solve these discrete equations, typically we like linear algebraic equations. If you're able to do that, fine. But they can also get very large. So then we go one step further and ask the question, can I reduce this further? And there's a clue here saying that, well, I got the discretization at one level from projecting onto a basis. So maybe a proper choice of basis would do it. Okay, so this is just a very quick idea of tying with what we have been talking about so far. Just referring back to one of the earlier conversations. So the essential, but you've seen that defining that properly is an issue, right? So you saw an example where a very localized density variation can atmosphere. So how do we get those basis vectors? We prefer that they are orthogonal. So normally you go through a process, right? Traditionally, this goes back 50, 60 years to POD. I won't go through the story of POD. Instead, what I will do is I will tell you that we will use singular value decomposition in order to get our POD vectors. So if you now have data that comes either from experiment or comes from computation, so a lot of people have been talking about either the data that they generate from the modeling, you heard quite a bit of it a little earlier, or from measurements that they make and right that they get from various instruments all over the world. So using that data, you would construct this matrix A, right? As I said, I'm not going to get into the details of how you go about doing that, but let's just say you capture it as a matrix A. This matrix tends to be a tall and skinny matrix, meaning that in the example that I'm going to give you, I have 132,000, that is 132,000 rows and 1024 columns. So you can just imagine that, and this is a small matrix to start with. U here, in this product, is an orthogonal matrix, as is V. U is the matrix that I'm interested in. Sigma is a diagonal matrix. The entries of sigma are called the singular values. They usually show up in a decreasing order. You can interpret, for those of you who want, you can interpret it as an energy. The the magnitude of that diagonal vector represents the total energy in the system. So you can imagine that if they are appearing in a decreasing order, that if you say take the first 5 or first 10, you can ask yourself the question if it captures 99% of the energy involved. Is that enough? And do I really need the remaining, right? If there are remaining 1,000, if I have 24 of them, do I really need the remaining 1,000? So the question is that, is there a value R, right, at which I can just basically stop, which means that this sigma effectively corresponds to each of the sigmas corresponds to the energy that's there in one of these basis vectors, which makes up the columns of U. So what I'm saying is, if it's enough to take R of them, then it's enough to take R basis vectors for you to essentially capture the dynamics, we hope, of the system that you have at hand. So just as a crude illustration, so you could reconstruct an approximation to AR by taking, so if I, like I said, if you say that the first 24 singular values capture most of the energy, so R would be 24, so you take 24 column vectors, right? And you take 24 row vectors there, and you get a M by N, again an M by N matrix AR, which is an approximation to A. Okay. You could also, of course, project. You could use the Galerkin approach and project your governing equations onto this basis vector, which was my motivating story in the beginning, and get a discrete set which is much, much, much smaller than what you had when you started off by saying, let me use, say, Fourier series or hat functions, box functions, or whatever it is. The problem is that you're trying to save on computation there, whereas SVD itself could be, in the case N is 1024 and M is 132,000. Obviously, you would choose, right? The scheme is going to be, you're going to do it in a fashion that it is Mn squared, that is 132 billion. So, like I said, this is a pretty small. This problem came from a 256 by 256 two-dimensional grid from a CFD code, having U and V velocity components. So, a relatively small problem. So, data sizes get very large. So, the cost of SVD grows very quickly. You need to do something about that. Okay, so yeah, Professor Vinita and I have been working on this, as I said. So there are two papers that I'll talk about. One that she and I have put out. It's here is the reference. It's on archive.org. So this is a hierarchical scheme. So basically, what we do is you take the matrix that you have. I've shown them as blocks, and you break them up into blocks. So you can do SVD of each of the individual blocks. And because the blocks are now small, Mn squared is a much, much, much smaller value, the amount of computation that you do. And we have basically developed a scheme by which you can merge two sets of columns, right? So you have two blocks adjacent to each other. We've come up with a merge and truncate mechanism by which you can merge the two to form a larger set. But the number of vectors in there will always be determined by either you a priori say I want 10 basis vectors, or you give me a measure, a truncation, saying that the largest mechanism by which we can censor the largest eigen, what do you call it, singular value to the smallest singular value. What is the relationship? Maybe the ratio is 100 or something of that sort. So based on that, we not only merge, but we also truncate. That is, we throw away singular values that come along, that are we discard singular values that come along that are smaller than say 1/100th of the largest singular values. So that process is repeated and in a systematic fashion, so that eventually what you're essentially going to do is you're going to be left with a situation where you can do now a merger between the individual rows that you've merged to form, right? Now you can do a merger in the column-wise direction, so that you essentially at the end of it end up with the singular value decomposition, but to the required, what should I say, precision that you are asking for, required tolerance that you're asking for. So that big matrix that I was talking about, I'm not sure whether this is clear. This is 8 by 8. Let me just read that out. Whereas this is 512 by 512, and they cycle through. These are the block sizes, and as the block sizes increase, as you can see, if one of them is too small, then the computational cost is large. The overhead of all the merger, truncation, you know what I'm saying, that is not amortized. But once the block sizes get reasonably large, you get to an optimal point where there is a pretty big speed up. And I decided to present sort of at one level the worst case scenario here. This is the serial code. This is the speed up. This factor of 6 that you're seeing here is the speed up that you're when the code is run in a serial fashion, and not the merger and all of that can be done in parallel. It is not. There's no parallelization involved. So the idea would be that if you have an enormous data file, yes, you want the POD. It's very easy, relatively easy to do, even if it is in fact larger than the amount of RAM that you have. The second thing that I wanted to do, this is work done by Charumati under my guidance, along with Professor Vinita, and I are the thesis advisors. So she is following a different object. No, this is an extension from our divide and conquer. So there is this notion that you project onto you do a random projection, project onto a matrix that will shrink the size, or you do random sampling. So the difference between what is traditionally done, what others do for random sampling, and what we do is, we now have a scheme by which if you give me a U that corresponds to one sample and you give me a U that corresponds to another sample, I have a mechanism by which I can merge them and do a truncation to the precision that you're asking, the tolerances that you're asking for. So very quickly, so the data that I was talking about, the velocity, 2D velocity data, doing that, we got speed ups of the order of 31. There's a lot, as I said, I didn't want to get into a lot of parameters, so a lot of the labeling and all that I've removed just so that there's no confusion. The C1, C2, C3 here correspond to sampling sizes that are close to the size of the matrix itself, sampling sizes that are about half the size of the original matrix, and sampling sizes which are very small. And as you would expect, if the number of singular values and these vectors that you're asking for are small, then you get an enormous amount of speed up. If you want a larger number, yes, then it does take much more. It does take, you don't get as high a speed up. What we have done, what we have also done, a lot of the POD and especially singular value decomposition based schemes, they're evaluated based only on the single values. People measure against the singular values and they're satisfied with that very often. But in reality, you have to look at these vectors and see whether the angles that you're getting, right? So we have a mechanism by which we can use the cosine of the angle to figure out whether it has converged or not. And so there is an incremental process through which we can actually build up. So that's the deal. So we sample, test. Does it meet the criterion? Sample more. So that would be the process that we would actually do. Okay, I think maybe at this point I will stop here. So, but the deal is, my hope, I mean, the message that I have is, my hope is that listening to all of you guys, we are a bit excited. We are hoping that we'll start getting data, or we'll have access to data that is in terabytes rather than in gigabytes. So, and hopefully are able to contribute something to GFL in terms of the physical understanding that comes from these POD modes, and also their use in actually modeling and simulation. Thank you very much.
Thank you. Thanks a lot, Balaji, Louis, and Emma. So I'm sure we'll have an opportunity to discuss on Monday next week. May I now request Anubhav Roy. So we will skip the 7-minute discussion period we have in the interest of time. So we'll directly move on to Anubhav Roy's talk on waves and instabilities in particle-laden flows. Anubhav Roy is at IIT Madras. Anubhav?
Are you able to hear me?
Yeah.
Okay, thank you. Hello, everyone. Today, I'll just give an overview of things that we are doing as part of the GFL initiative, focusing on waves and instabilities in the context of particle-laden flows. So one of my interests is basically studying particle-laden flows, especially in the context of geophysical flows. And here, what we have in mind is a dispersed phase in a fluid, which you would find in a wide range of problems of both oceanic and atmospheric problems. And here, even though the particulate phase that we're talking about is minuscule in size, in some cases of the order of few microns, they can have a large scale impact. So as an interest of time, I'll just focus on the bottom part, which is looking at particle-laden flows, which are primarily of the oceanic interest. So the thing that I would like to show here are examples of shallow particle-laden flows. So we all have familiarity with shallow water waves. These are basically shallow scenarios of flows with there being a particulate phase. So you have on the top right case a dam break problem. Then you have a granular avalanche that's there on the top right case. Then you have in the bottom left, there is a viscous fingering, where the classical Saffman-Taylor instability of trying to pump a low viscous fluid into a high viscous fluid gives rise to this beautiful fingering pattern. Here, what you are trying to do is you're trying to pump a fluid, displace the clear fluid with a particle-rich fluid, and that actually gives rise to this pattern. The last one is an example of sediment transport. So you have an oscillatory flow over a wavy bed, and you try to see that how does this kind of a flow pattern lead to the change in the transport. So before we actually look into the waves and their coupling with the particulate phase, I mean, whenever we talk about motions of particle, a key thing is to identify it in terms of this parameter space of 3 non-dimensional numbers. So I'll just focus on problems with respect to this. There is the flow time scale, which helps us actually decide these 3 non-dimensional numbers: the Reynolds number, the Peclet number, and the Stokes number. So if I were to understand the viscous relaxation of the fluid with respect to the flow time scale, that gives me my Reynolds number. So high Reynolds number flow, particulate flow would be basically bubbly flows. If I have the particle relaxation, that the particle loses its inertia and it takes substantial amount of time, fairly massive particle, that would give me my Stokes number, and granular flows are classic examples of that. Then I have the regime. So the vertical axis is actually inverse of Peclet. So if I go up the axis, I'm basically going to smaller values of Peclet, systems which are very close to equilibrium. So these are more industrial problems rather than being geophysical. But this is what we will start with to get some insight. That's the colloidal suspension problem. And the origin is where you have the Stokes and Reynolds basically being 0. So both fluid and particle inertia is negligible. But then the thermal forces are almost absent. These are athermal systems, which would typically be the case of a lot of bacterial motion, planktonic case in terms of oceanic flows. So the first thing we would be looking at is a classic problem of a gravity-driven film. And this is a film which is particle laden. So the first question, as I said, we are looking at a regime where the particle inertia is negligible, fluid inertia is also small, and the Peclet number is also modest, it's not large. So in this case, the only role the particulate phase plays is actually modulating the viscosity, and its diffusivity also being concentration dependent. Now, this is a very classical problem for the clear fluid problem. So this is if you were to observe fluid trickling down your window pane, you would see these roll waves forming. I mean, here is an example that you would see on a rainy day on a slight slant road. You would see these forms, these traveling waves occurring. And this is what is known as the Kapitza instability for a falling film. And the linear stability calculations were done by Benjamin and Lee, trying to find out the threshold for this viscous instability. Now, if you do this with the Brownian particle, the result is as expected, that particles stabilize the flow. There is nothing. So here is a phase after doing the entire eigenvalue calculation. When you plot it in the phase space of the wavelength of disturbances, k is the wave number. So the inverse of the wavelength is the vertical axis, and the Reynolds number of the flow. You find that as the volume fraction increases, there are two modes in the problem. One is the surface mode that I just spoke about, and then there is a shear mode, the Tolman-Schlichting instability that happens in Poiseuille flow or a boundary layer flow. So these actually get dampened due to the presence of the particulate phase. This is expected, I say, because you increase the concentration of particle, you are enhancing the viscosity. So effectively, you're basically having a large Reynolds number in the problem. So you can go ahead and try to do a nonlinear long wave theory of this problem, where you assume a small parameter, which is the wavelength, basically being much larger than the thickness of the film. And you would get a nonlinear wave equation, describe the motion of these in the nonlinear regime. But then still, if you were to look at experimental observation, so in the bottom panel here, you see experiments of free surface flows with particle in it. And as you see that when the concentration of particle increases, the picture actually shows that the surface corrugations are getting more pronounced, which means that particle somehow is enhancing the instability, just in contradiction to what I just said in the earlier explanation. So the reason this actually happens, the picture which the previous picture was insufficient, was that when you have the particle becoming more athermal, you have a contribution due to particle interaction, that is the non-equilibrium contribution. And this leads to essentially one key thing that it leads to, that particles tend to migrate towards regions of low shear stress. This is known as shear induced migration. And here you see a picture where this is like a boundary layer developing flow. You have a plug that is released, and the film actually flows down. So it fattens up as it flows down. And initially the concentration is uniform, and gradually you see a concentration where there is particle rich on top and particle deficit at the bottom, which immediately tells you that this is like a viscosity stratification. And a viscosity stratification of this kind would lead to a destabilization. So this is what I'm just showing here for the surface and the shear mode. Now, this is all where we have said that the particle inertia is completely ignored. There is no inertia of the particle, and obviously we're ignoring the fluid inertia. But if we were thinking of sediment transport, or even if you're thinking of sprays, so spray is basically a droplet-rich boundary layer on top of the ocean surface. These are modest to high particle inertia problems. You have drops in air, or you have sediment in water. These usually will not be a small Stokes number. So before we think of problems with free surface and the complicated aspect of free surface, we set out looking at a problem. So this is in collaboration with Professor Kasboi at Arizona State University, where we were looking at just a single vortex. So a single vortex stability is one of the most well-studied problems in stability of fluid flows, and it is known to be stable. There is nothing that happens to just a single vortex. Whether you include effects of viscosity, it still remains stable, it just dampens it. Now, we have a vortex which is seeded with particles, those are inertial. And the moment you let it evolve, the particles get centrifuged out. But because there is a coupling between the carrier the fluid phase and the particulate phase, this actually destabilizes the vortex. The vortex basically becomes unstable, which you can see from a rough way to quantify this is looking at the vorticity contours or the velocity contours. There are these striations and waves which subsequently become nonlinear. So this is an Euler-Lagrange DNS. So you solve the fluid flow field using an Eulerian method, and then you basically solve for the particulate field discretely using Newton's laws of motion. Basically, an equation where it is the acceleration is equated to the drag of the fluid. But if you want to do a stability analysis, that's a complicated system to work with because it's a mixed system. So if I want to understand the origin of the stability and also quantify it, I need to bring it back to an Euler-Euler system. So which is where we work with a model that is a single fluid model, where you write down it in terms of a single fluid. And the part that I want you to notice is this looks like an equation which is similar to a buoyancy-driven flows, where you have a density field that is actually there. But there is an interesting term which appears here, and that term which is circled out, that's a term that can actually act as a source or a sink based on whether it's a vorticity or a strain-dominated region. So this is known as preferential concentration, that particles, because of their inertia, tend to sample regions of flow differentially. So we can then, now we have the scope of actually doing a calculation of quantifying this growth rate. So we go ahead and try to do a linear stability calculation for this particular problem. And there is a reasonable comparison that we have from the DNS, which is an Euler-Lagrange DNS. So I want to just bring this, this is not a comparison done between a DNS of just an Eulerian problem. So which is where actually understanding what is a growth rate also becomes tricky in this particular scenario. So with this, I would like to end that as part of this initiative, we are quite excited to look at how dispersed phase can modulate instabilities, and in some cases possibly introduce new ones. We are also interested in understanding, so everything that I spoke about right now till this point was trying to look at the entire phase of the particle. Like, we are not looking at individual particle transport, but then individual particle transport in wave fields is also something that's an exciting field that's coming up. And especially when the particles are anisotropic in nature, the geometry plays a role of how they respond to the wave field. With money, we have been looking at wave interactions in stratified shear flows. So there's no particle here, but just basically looking at how internal gravity waves due to background shear non-linearly interact. And finally, just as a lead on for the next talk of my collaborator, Housam, he's going to talk about geophysical turbulence, particle-laden turbulence. So one of the things that we are excited is trying to see that how we can look at better particulate transport in geophysical turbulence, and trying to see if we can compare Euler-Lagrange DNS with Euler-Euler models. Thank you.
Thanks, Anubhav. If you don't mind, we will have the discussions later. And I may now invite Mohammad Hossam Kasboui from Arizona State University to talk about his work on computations in geophysical particle-laden turbulence.
Let's see. All right, is this working?
Yeah.
Okay. So I want to start by saying thank you to Mani and Anubhav for involving me in this effort. Anubhav did a really great job motivating the subject. So what I will do is focus primarily on the high fidelity computational methods that we use and develop in my group. All right, so our interest is in particle-laden flows and turbulent particle-laden flows. So there are a bunch of examples that I can talk about in terms of geophysical flows. What I will say is that I live in Arizona in the Sonoran Desert. So dust devils are definitely a common sight driving down the freeway. We also get a lot of these sandstorms that we call haboob. And this is one of the leading causes for car accident, because when this happens, it's very sudden. People don't get a warning ahead of time, and visibility drops very, very suddenly on the highway. So this causes some issues. And another interest in these flows stems from our interest in seafloor erosion, particularly in the context of the rise of sea levels. So the general questions that we ask when looking at these flows are going to be like this. So how do particles modify the structure of turbulence in dusty flows? And this is not trivial because the particle phase has complicated dynamics. And the other question is going to be for sediment transport, what is the role of turbulence? How does it enhance the seafloor erosion or maybe reduce it? Okay, so this is in terms of geophysical applications, but there are also a number of reasons to look at these flows in engineering contexts. So traditionally, people have looked at particle-laden flows in sprays, So you have these sorts of sprays in jet engines, and you want to understand what happens to spray droplets, because that makes a difference for how well they burn. Another interest is in this application, that's brownout, which happens when you have rotorcraft landing on a desert seafloor. This also happens in powered landings. This is a video of the Perseverance rover that landed on the surface of Mars in 2021, so earlier this year. And what you can see is here is that the rockets on this device called the Sky Crane basically lifts up all the dust, and this causes the thick dust cloud to form, which in previous powered landings on Mars interfered with velocity sensors and so on. So, and this could also create a crater in the Martian floor if it's not stable enough. This could also lead to issues with dust ingestion in engines and so on. Okay, so many reasons why to look at these flows. Turns out that they are really complicated to model. The reason is because it's a highly multi-scale problem. So you have on the smallest scale, which is what we call the microscale, it's on the scale of individual particles. So this is the micron scale. You have particles that are moving according to relatively simple equations of motions. You have the Newton's second law. Particles may bump into each other. They feel a fluid drag. But when you zoom out to what we call the mesoscale, which is the millimeter or centimeter scale, what you see happening is that the particle phase may behave as sort of fluid, but a fluid that's highly compressible because particles may be able to form clusters, right? So these clusters are essentially shocks in the particle phase. And then when you move out, zoom out, you also get to the macro scale, and you also have these clusters that persist on the macro scale. These are, by the way, pictures from a fluidized bed experiment. So how do we approach this problem? Well, our research approach consists in using theory, computational engineering, and numerical methods. So today I'll focus primarily on the numerical methods that we use in our group. Now, as I was telling you, there are at least 3 scales of this problem. You have the microscale, the mesoscale, and the macro scale. And clearly, no single computational tool is going to be able to describe all scales simultaneously. So what we use here is 3 different computational methods. So the first one is called resolved particles direct numerical simulation, where the flow around individual particles is resolved. Particles are treated as immersed boundary methods. And when doing so, you can track order 100 to 1,000 particles. So this is a method that we're actively working on. Another method that we use is what's called Euler-Lagrange method, where basically you treat particles as individual points that you track in your flow field. This is a very powerful method, and so far we can treat order billion particles in some of our largest simulations. And next you have an Euler methods, which is just a fancy way of saying continuum methods, where basically the particle phase is treated as a continuum, but this requires closures and appropriate models that for certain regimes are not working very well. All right, so I'll talk first about the Euler-Lagrange method since it's the easiest to introduce. Basically, this is particle tracking method. So we solve the equations of motion of every individual particle, right? So change of position is due to the velocity, and change of velocity is due to forces exerted on the particle. So you have hydrodynamic forces, you have collision force, you have gravity. The fluid phase is treated in this fashion, and this is based on the volume filter description of Anderson and Jackson from 1967. So you have incompressible fluid, and you have this momentum mass conservation equation, and then you have this momentum conservation equation. You have fluid volume fraction that shows up, and you also have the interface coupling between the particles and the fluid that shows up through this term. Okay, so I'm not going to dig too much into the computational method. Instead, I will show you some applications of it. So one of the first applications is studying the erosion of seafloors. So Anubhav showed a video that looked somewhat like this from experiments, some Singaporean lab, I guess. But basically, the reason why we're looking at this is because people have figured out that if you have a naked seafloor like this, then you have the erosion of the seafloor. So you have these sand grains that are suspended and lifted and washed away. And then the realization is that if you plant some stuff, seagrass or mangroves, then you may have a stabilization of the seafloor. But there is also contradictory evidence saying that for certain plants that you may have, you would actually increase the erosion of the seafloor. So that's what we're trying to understand. This is just a visualization of one of our simulations. We don't have any kind of vegetation here, so this is just an oscillatory boundary layer with Lagrangian particles. Another application which has more of an engineering relevance is to look at what drag reduction you may get by including spherical particles. So this is a simulation that I'm showing here. So the top part shows volume fraction, the bottom part shows the velocity magnitude. And basically what we do is introduce particles of different sizes, so 90 to 350 micron water droplets in a carrier phase, which is air, and look at the change in the skin friction drag, right? So we find that certain particles increase drag, other particles reduce drag. This has implications in terms of pipeline transport, because anything that reduces drag is going to lead to energy savings. So now I'm talking about the continuum models. So the fancy name is kinetic-based Euler methods. The way these methods are derived is, contrary to the two-fluid method, which a lot of people would be familiar with. The way this is derived is by starting with the Boltzmann equation. So you have this population balance equation in phase space, where you have F here is the number density probability distribution function. And then what you do is that instead of solving this equation in phase space, which would be very difficult and computationally expensive to do it, you solve moments of this number density PDF, right? So the 0th order moment is going to be the number density. The 1st order moment is going to be the particle momentum. The 2nd order moment is the energy tensor. The 3rd order moment is the heat flux, and so on. So when you write equations like this for each of the moments, you realize that the conservation equation for number density here is going to depend on the momentum. The conservation equation of momentum is going to depend on the next order, which is the energy. And the conservation of energy is also going to depend on the third moment, which is the heat flux. So there's a closure problem that needs to be addressed here. And the way it's addressed in our method is using a presumed PDF approach. So we'll typically assume something like this, that the number density PDF looks like an anisotropic Gaussian. And this is neat because it's parameterized by the particle pressure, which is basically covariance of the particle velocity, covariance of the particle velocity. So when the particle pressure is 0, basically this is saying that all particles within a cell have the same velocity, and this PDF collapses onto the monokinetic distribution, and all the equations that I showed previously become just your regular two-fluid model. When the particle pressure becomes isotropic, so converts to something like temperature times the identity matrix, then this becomes the Maxwellian distribution, which is appropriate for very dense flows. And if the particle pressure is not 0, not isotropic, then this method at least allows us to capture particle trajectory crossing, which refers to the fact that within one cell, you may have different velocities for the particles. Okay, so we use this method to understand the genesis of clusters in these particle laden flows. So here what I'm showing is homogeneously sheared suspension that's also subject to gravity and initially perturbed. Basically, these are two simulations in Euler-Lagrange and Euler-Error method. The particles are the yellow dots. And you can see that we can reproduce, for the most part, the same behaviors in Euler-Lagrange and Euler method. Right, so another project where we use this approach is understanding turbulence modulation by inertial particles. So for this project, we looked at homogeneously sheared turbulence. And we seeded this turbulent field with various particles, 50 micron particles and 90 micron particles suspended in air. So what I'm showing here is the single phase simulations. And what happens is because you have, so this is the initial homogeneous isotropic field, and because of the shear, what happens is things are getting sheared and the turbulence becomes anisotropic. Now, when we add the particles, then we see that the 50 micron particles enhance turbulence and the 90 micron particles attenuate turbulence. This is, the colorful fields are magnitudes of vorticity. And here I'm also showing a comparison between Euler simulations and Euler-Lagrange simulations. And again, we reproduce primarily the same features between the two classes of methods. Okay, so the last class of method that I want to talk about is resolved particle direct numerical simulations. This is based on a volume filtering immersed boundary method where basically you add, there is a fancy derivation, but this results in another term to the right-hand side of the momentum equation that enforces the no-slip boundary conditions. So we looked at this originally because we were interested in these stirred flows and interested in doing some comparisons. And now we're adopting this to simulations where you have a large number of these resolved particles. So I'll just skip this. So this is still work in progress. Here I'm showing comparisons with the Schiller-Neumann direct correlation for an isolated sphere. And this is initial simulation where we're tracking, if I recall, 100 of such resolved particles. All right, so I'll leave you the conclusion slide. If you have any questions, feel free to ask me now or maybe talk later.
Thank you, Uzam, for that informative talk. I'm sure we will have an opportunity to discuss on Monday next week. Thanks again. May I now invite Thierry Doxua from ENS Lyon to give a talk on laboratory studies of internal waves. Thierry?
Yes. So do you see my screen? It's okay?
Yes. Yeah.
Okay. Hello to everybody. So I will speak today about what can be done in the lab with regard to internal waves, and trying to show that studies in the lab could be quite complementary to more oceanographic studies. So I think we can play with internal waves and use the lab to illustrate, as in that case, what are internal waves, what are interferential waves in that case, with the generation of underwater tsunamis because of the motion of this boat. But we can go much further and we can discover new mechanisms that could be useful to understand from the knowledge, but that could be at play also within the ocean maybe. So let me show you a few examples. But before this, I would like to emphasize that a small revolution was possible because of the invention of a novel way to generate internal waves. Before, you could use a cylinder, an oscillating cylinder, and generate the central screws with 4 different beams. that were not very well defined, quite complicated from the theoretical point of view. You could use a paddle light generator or a parametric excitation that are very nice ideas to generate waves, but that you cannot really control, as I will show using the next and novel way. So the idea was proposed by Louis Gostio, who is around the table doing his PhD thesis in collaboration with Henri Didel and Samuel Versier, where you use camshaft, and because of this camshaft, it's possible to generate a boundary condition of oscillating plates. And because of this, you can generate quite well collimated and well-defined beam that is very close to what theoreticians would like to have in a lab to test theoretical ideas. So for example, you can see on the next case that if you put such a generator on the top of a stratified tank, because of the oscillating plates that will oscillate in that case vertically, you can generate a sinusoidal pattern and generate a beam that is quite well controlled, and you can study its propagation and maybe its instability and test theoretical ideas. So I would like to emphasize that not only you can check and test theoretical ideas, but you could also find the importance of new effects. And in that slide, I would like to emphasize 4 different mechanisms that were studied and discovered recently by our group of colleagues. And I think this is 4 examples of cases where experiments are useful. The first one was mean flow generation that has been discovered by D.M. Bord during his PhD thesis almost 10 years ago. The idea was to put such a generator in a 3D tank. And because of so you see the generator within the tank, which is generating a beam well defined in 2D, but because of the 3D situation, because of the viscosity that plays quite an important role, and because of the nonlinearity, there is a generation of a mean flow. And you see on the right the top view of what you could see if you put dye particles. So the generation of vortices, which is quite strong, and that you can see an evolution of its amplitude of the mean flow, which is quite important. And more recently, in the work by Timothée Jamin and with a group of Triantafilus aquilas, it has been possible to show that theoretically we can understand this effect that was initially discovered experimentally. So the idea is that nonlinearity, viscosity, and 3D effect could be important was not anticipated at this importance. At least even very well-known researcher was surprised at the beginning. The second effect is related to the parametric subharmonic instability. This is a work that has been found by Baptiste Bourget, another PhD student, using the setup that I just explained. He showed that because in the parametric subharmonic instability, you have a main beam with a main frequency omega naught, which is able to generate 2 different daughter waves, subharmonic waves, which have different frequencies and so a different angle of propagation. The angle of propagation being different from the angle of inclination of the beam. They are generated on the side of the beam. The interaction is different, and because of this, the growth of this subharmonic wave is smaller than theoretically expected initially. And so you understand that if you consider a finite width beam with respect to a full plane wave, the first one is less unstable, and it explains why we initially had a discrepancy between theoretical prediction and experimental verification. So this has been performed experimentally by Baptiste Bourget and co-workers, and the work has been derived analytically in our paper, but more beautifully by Triantafilus aquilas and his PhD student, or his former PhD student, Hussein Karimi. A third example to show, which is much more recent, the effect was initially discovered by Mani and his PhD student, or his former PhD student, Dheeraj Varma, with their collaborator Shalamala. If you put in a tank, and at the bottom there are 2 different experimental measurements of what was predicted by Mani and Dheeraj. If you send a beam, a vertical mode, at a frequency omega naught, depending on the condition, you can see a clear super harmonic generation, and you see the generation at 2 omega naught of a beam which is different, and that could extract a lot of energy from the initial beam. So this is an important instability that you have to be able to understand. And Pauline Husseini and Dheeraj Verma in the experiment were able to match most of the results experimentally. The fourth one is maybe not so important, but quite useful and interesting, is a work by Leo Mas, who was able to show for the first time more than 25 years ago the possibility to have internal wave attractors, the possibility to attract along a limit cycle energy at a very concentrated way. And we showed that these internal wave attractors were stable, and it was not, a posteriori, it's quite evident because the energy is focused, but it was not thought before, and it explains maybe the reason why it's difficult to see this object in the ocean. So just to go beyond, it's possible to go beyond a very simple and very simplified experiment. You can take into account rotation and the Coriolis force. This is typically what we get, and this is an experiment that Corentin Pacari now is doing in our lab, studying this setup. It's possible also to get rid of the very strong dissipation, which is an additional ingredient that you would like to get rid of. So you can use a larger platform if your system is well understood. So typically in Grenoble, they have this beautiful new Coriolis platform which is quite large, 13 meters in diameter, and with a lot of water and 2 tons of salt. You can study a large system, so quite large Reynolds, not as large as you would like, but quite, you can get interesting regimes and in rotation. So this is typically a place where it's possible to study more realistic internal waves lab experiments. And this is an example that several people around the table were involved, especially Sassan and Louis Gostio. In that case, the idea was trying to reproduce most of the different physical mechanisms that are at play in the generation of internal tides and along the Luzon Strait. So it's possible in this very large platform to generate tides, to have in the center a bathymetry, which in that case was prepared as close as possible to the system between Philippines and Taiwan, and we were able to show the different steps between the generation of internal tides to the generation of solitons. So just to conclude, I would like to emphasize that the physicist approach could be quite complementary to that of oceanographers, as biophysicists are useful to understand biology. The idea is to distinguish the different mechanisms. For example, generation and propagation of internal waves are more or less well understood. There are a few questions, but not so much. The second point, which is much open and still open, is a dissipation mechanism that are still debated. There were a few experiments, numerically or experimentally, that begin to clarify our point of view, but there are still important questions related to instabilities. Nowadays, what we are interested in is the importance of the energy spectra, how we could explain the richness of the energy spectra within an ocean. Can we detect and can we reproduce similar things in the lab? These are still open questions and quite important. So this is more or less what I wanted to say. This is some picture of the group around us, but there are many other people who are involved in the different experiments that I just schematically described. Thank you very much.
Thank you, Thierry. I will look forward to our discussions next week. In the interest of time, I will just move to the next talk. Thanks again, Thierry.
Thank you.
We'll see you on Monday. So may I now invite Louis Gostio, Andrea Maffioli, and Helen Scolan from École Centrale de Lyon to give their talk on experiments on mixing and turbulence in stratified flows. Yeah, Louis or Andrea?
Yeah, I'm trying to share the screen.
Okay.
I'm having a little issue. Should be fine. There we are. Can you see the slides fine?
Yes.
Great. Okay, so good afternoon and good evening and good morning for some. So I'm Andrea Baffioli, and today I'll be talking about some work with Louis Gostio and Hélène Scollon, which has been focusing on theory simulations and experiments on turbulence in stratified fluids. And so to begin with, I'd like to talk to you about stratified turbulence and two, I think, very useful, very different approaches which exist to study it. The first one is called strongly stratified turbulence. It's the one I'm most familiar with. In short, it's SST. So this is the first and probably last talk, which has SST not as sea surface temperature. I'm sorry about that. So it's a scaling theory which has come up over the last 20 years or so to describe turbulence in the limit of a very strong stratification, so a very small horizontal Froude number, and concurrently a very high buoyancy Reynolds number. So this gives rise to the flow that you can see at the top, which is a vertical slice through a DNS by Bertauer et al. So you can see basically the formation of horizontal layers. And the theory was successful in predicting the layer height, which is should scale as UH over N, where UH is a typical horizontal velocity. And moreover, the layers are energetic enough to undergo shear instability, which is a means by which this flow can lead to 3D turbulent patches and eventually dissipate the energy it has. In subsequent years, Lindbergh has predicted energy spectra, which are 1D spectra because the flow is anisotropic in the horizontal and vertical directions. However, the DNS actually hasn't really been in agreement with such predictions, so there is a little bit of a gap there. And more recently, there has been work by Lindbergh and by myself and Bertauer focusing on the mixing efficiency, because this is a rather important topic in ocean turbulence. And so we have found that the mixing coefficient gamma, defined as the dissipation of potential energy over the dissipation of kinetic energy, is order 1, both theoretically and in DNS. And so this is kind of nice because the ocean value is, of course, gamma equals 0.2. So this is at least consistent. So the second approach, which is really widespread in the literature, is an approach which, for want of a better term, I'm calling single overturn model, which basically treats stratified turbulence as an ensemble of shear layers undergoing Kelvin-Helmholtz or Humboldt instability. So there's been a hint of this in the talk by Jennifer McKinnon earlier today. And within this literature, the KH and Humboldt instabilities are treated as atoms of stratified turbulence. And what's behind this statement is that we can understand the flow by understanding these instabilities. And there is a lot of literature on experiments and numerical simulations about this canonical problem, really. And there is empirical evidence that gamma adjusts to the value gamma equals 0.2. So again, we have this famous value, which is then also observed in the ocean. And there have been more recent efforts aimed at quantifying the variability of the mixing coefficient during the whole lifetime of a shear layer, with respect to non-dimensional parameters, which are basically the buoyancy Reynolds number, a gradient Richardson number, or a Froude number. So these are really slightly different approaches, but I believe that both of them attempt to model ocean turbulence. So the question we should really be asking is, what does ocean turbulence look like? Does it look like any of these two canonical problems? And so here I show some observations made by Louis and by Van Haan and Chimotoribus, which, excuse me, show the temperature field above Mount Josephine, which is an underwater seamount in the Atlantic. And so in the bottom panel, what you can see is temperature as a function of depth and of time. And you can see a vigorous turbulent event. But if you then look at a longer time scale on the top panel, what you can see is that this flow is tidally forced. And more interestingly, from my point of view, the second and third panels show the Thorpe displacements and the kinetic energy dissipation rate as a function of time. And really, you can notice the patchiness of the turbulence. And the dissipation rate varies by more than 3 orders of magnitude. So we really have a strong spatiotemporal variability, which neither of the two previous approaches really captures. So we're looking to go into this a bit further. So now over to Louis for some experimental work.
Thank you, Andrea. So as far as experiments are concerned, we have been trying to deal with the issue of mixing stratified turbulence by means of global energy budget. So as an illustration here, you have a sketch of the historical Joule experiment. You have a vessel with a steerer inside, which is filled with water. And it was the first time you could accurately estimate the transfer from mechanical energy to heat. So the elevation of temperature is the fluid. In the fluid was giving you an integrated value of the viscous dissipation in the reservoir. But what we would like to know is what would happen in a stratified version of this Joule experiment, and basically which proportion of energy would go into heat and which proportion of energy would go to irreversible mixing. So the first academic device that we have used is a lock exchange experiment. So basically you have two fluids of different densities, a gate between the two fluids. You open the gate, you have two counter-propagating gravity currents. And it's an interesting setup because simply by measuring density profiles at rest, you can have a complete estimate of the energies involved in the system. You have either the input of energy, which is available potential energy, but also, as you can see in the upper right panel, the red curves shows the irreversible increase of the background potential energy here. And by reaching the final state, you have a very accurate estimate of the integrated cumulative mixing efficiency in this system. So it can be computed for different values of the hydraulic Reynolds number, as you see in the bottom right panel. And we reach a state which becomes Reynolds independent for high values of the Reynolds number, and that saturates at the values of mixing efficiency up to 0.25. But this setup by essence works at a fixed Richardson number because we are dealing with the gravity currents. So if you want to vary the Richardson number, you have to change your forcing. So you can do this by towing a regular grid in a linearly stratified fluid. So doing so, you can impose your initial Richardson number. These are still decaying turbulence experiment that we perform here. And again, by measuring the increase of background potential energy, we have an estimate of the cumulative mixing efficiency. So this efficiency is found to be proportional to the Richardson number at low values of Richardson number. But in this system, you still have 1 degree of freedom, which is the buoyancy Reynolds number. And this number, in the case of decaying turbulence, tends to decrease when the Richardson number increases above 1. And this is an experimental limitation that it's very hard to overcome. So to complete this energetic budget, we also perform direct numerical simulation of this decaying stratified mixing experiment. The particularity is that we have resolved in time all the fluxes between the different energy reservoirs of the system. So you see an example of one realization on the right panel with different colors for different reservoirs. The yellow and green curves correspond to the mechanical energy, so the kinetic and available potential energy that tend to go to zero when everything is dissipated. And what's interesting is that we can split the dissipation between what goes to heat, this is the gray part of the curve, and which is explicitly computed in the simulation, and what goes again to the increase of background potential energy, which is the irreversible part of mixing. So to summarize these different results, first we have a good agreement between this last presented DNS in gray and the towed grid experiments here in red in terms of variation of mixing efficiency as a function of the Richardson number. But of course, this regime is fundamentally different than the strongly stratified turbulence that Andrea presented initially, which occurs at a high buoyancy Reynolds number. So this can be found in forced numerical simulation, like Andrea already performed. But I guess the question, the next question here is to know where and when does the oceanic turbulence correspond to one of these two extreme regimes. And I will let Andrea give a few words on the perspective of our collaboration.
Yes, so thanks, Louis. So the perspectives, so two quick slides about this. So I think it's quite exciting to move to something a bit different, to the two approaches I hinted at before, which are basically, in some sense, assume homogeneity, or at least have a missing part, because we do not know the spatial temporal distribution of, for example, KH instabilities for the single overturn model. So basically, we would like to focus on intermittency, both in DNS and in ocean observations. And this is an approach, this is an extension of an approach that has been used in the literature by Portwood et al. And basically here is the DNS with forcing that I've done, and you can see a vertical slice of the entropy field. It's in log scale, and you can see that there are over 7 orders of magnitude of variation. So the flow is highly intermittent, and there are dark patches of turbulence separated by more lighter quiescent layers. With a filtering operation, we can discriminate between what is turbulent and what isn't, which is the yellow parts in the right-hand figure. And so this is really powerful, because then we can start calculating volume fractions of these turbulent patches, which are then required, for example, for the KH instabilities, if we want to make global energy budgets, and also conditional averages to test some of the scaling theories of that exist, and potentially provide new ones. So this can be done in DNS and again in observations. This is a further work by Van Halen and Louis, where you have the temperature, high resolution temperature measurements above the Great Meteor Seamount. And it's rather nice because in the top panel, which is again temperature as a function of depth and time, you can see clearly a train of KH billows in the green part, but in general, there is a lot of activity. This can be seen more objectively with the Thorpe displacement in the bottom panel, which has been coarse-grained, and there is a threshold. And thereby, we can again reproduce turbulent patches and potentially start calculating interesting quantities over them, which I think is an interesting new avenue to go into, basically. Thank you. So over to you, Mani.
Thank you very much, Andrea and Louis. That was a very nice talk, and I hope we will be able to discuss more during the rest of this week and on Monday. Please do join us on Monday. So the last speaker, Sasan Saidi, is unable to join us today. He sent me his apologies, and he said he will surely join us for the discussion on Monday. So at this point, I think we are done with all the talks for today's sessions. But since we are well over the scheduled end time, I would leave the discussions for Monday. At this point, I would request everyone, for those of you who had questions during any of the talks, there wasn't much time to discuss, I know. If you could please mail me the questions or contact the speakers directly. I'm sure it would be possible to reply, but that would also be ideal material for us to take up for discussion on Monday. So this is any questions, including students and postdocs. If you had any questions at some point, please do mail me or the speakers directly. It would really help us with the discussion. So at this point, I would like to thank everyone and remind everyone about the panel discussion we will have at the same time on Monday, September 13th, the Monday. And till then, I will keep in touch with all the speakers during the next 2 or 3 days. Thank you very much.
Thank you, Mani.
Thanks, Mani.
Thank you. Thank you, Mani.
Thank you.